Hi, in this video I'll show you how to use a parallelogram to choose the right trigonometry for pretty much any forces problem. And by the way, do give it a look, even if you've tried using parallelograms before and decided you didn't like them at all. And this often happens. You might have decided that you prefer to stick with one triangle instead of two. And a single triangle can often be fine, and it is after all how you probably learnt to add and subtract vectors, as though the vectors are journeys, and then what we take to be the sum total of any two of them is just like going, as we say, as the crow flies, which is to say, a straight journey beginning and ending the same. And that's fine if it works for you, and if you never have any trouble deciding how to arrange the triangle. But with forces, that way the single triangle is missing a trick, which is that with a parallelogram you can always imagine the vector arrows as strings literally pulling, and in fact you draw them all as coming out from the same point, the same particle that they're pulling. And then it's totally natural and intuitive to see the middle string as having the same effect as the other two acting together. Imagine this one pulling at the same time this one is pulling. You know the particle will move roughly in this direction, somewhere in between. And then you can feel that the trigonometry is just going to make this more precise. Now you might have noticed a bit of cheek here. For a start, plenty of forces push, not pull. So that's a bit of poetic license. But also for the trigonometry to work as we feel it should, we must be pretending that the lengths of the strings depend somehow on how strongly they are pulling. Otherwise, how is trigonometry going to tell us the resulting direction of movement? And we don't normally make any such assumption. But yes, this is exactly what you do want to pretend. That you can see the strength of a pulling force in the length of the string pulling. And you'll find it's totally reliable, and you can feel sure that you've chosen the right trigonometry this way. Always sketch. It doesn't have to be a great sketch, something freehand or with a set square. Also go here to this drawing machine if it might help you at all for teaching or learning. And do let me know if it does, or if you have any questions or problems. Thanks. And now an example. Okay, in number 4 we've got conservation of momentum applying to various particles rushing around and colliding. Yeah. It's not only, trigonometry isn't the only good reason for drawing vectors as arrows. That they might all the vectors might be parallel, and it's still worth doing. Like back here in question 3, for example, we did say, didn't we, that the effect of the two 4 Newton forces here was totally represented by this resultant force, which was actually 6, wasn't it? Not 3. 3 was half of it. But it's still useful to say, okay, we've got pointing upwards, we've got 3 and then 6, and then this must be balanced, because we were told the particle wasn't moving, must be balanced by the weight of the particle, which must have been 9. Something similar is going on here in question 4. In question 3 you had various vectors comparing with each other in opposite directions on account of they were all applying to the same, acting on the same particle. Here we've got various particles with their own momentums, but each pair of particles can be considered as a system, and we can line the vectors up and do addition and subtraction on a similar basis as we did here. And one kind of diagram is this kind. So this one fits the first pair quite closely. We could say the momentum situation for A before the first collision is, well, let's put equals, if it's not ungainly to have a whole word there before the equals sign, if we can cope with that. A before, by which we mean the momentum of A before, that's going to be, what was it, 0.8 with a velocity of 6 eastward. So 0.8 times a velocity of 6, 6 eighths are 48. And then opposing that, in a sense, if we think of A and B as a system, we've got a certain amount of momentum heading east and a negative momentum heading east. In other words, a positive momentum heading west. But let's consider it all in one direction and sum them up. So let's say, what's the total momentum heading east? It's going to be 4.8 minus this momentum here. The total momentum of the pair of particles as a system is going to be this one here. So this vector wants to be negative. Particle B before, the momentum is 0.2 times minus 2, 0.4. So the total momentum of the system of this pair of particles taken eastward, heading east, left to right, is going to be 4.4. So this is one way of doing this kind of problem, saying okay, after the collision the total momentum of A plus B has still got to be 4.4, and everything else should pan out. And then we have to make everything else fit with that. Well, we're told that A after is 4, or rather 0.8 times 4. Let's be clear, that's 3.2. In other words, less than 4.4. So by this stage in the story, the eastward momentum of B is positive. And we can say that B after the event is going to be 0.2 times VB. Also, we can see that that's got to be, we might as well say in passing, that's got to be 4.4 minus 3.2, or 1.2, which will help, because we've got a result of VB equals 1.2 over 0.2, or 6. Okay, something similar for C and D, but D is stationary, so we might have a simpler picture. And also that we're told that they're coalescing and sticking together afterwards. So let's just simplify this by saying the momentum of C beforehand, and what's that, 0.3 times 5, so C I mean, we could say that C plus D before equals 0.3 times a velocity of 5 plus a zero momentum being 1.5. You might say, well, they haven't coalesced yet. Nonetheless, it's part of the principle here that as a system, C plus D had a total momentum. We're saying we're doing the same thing after, it's just that, well, they're both non-zero momentums. Okay, so C plus D after equals 1.5, but also we know it's going to be a total momentum of a total mass of 0.4 times whatever the velocity is. So we can solve that straight away as well, can't we? Let's do it here. The velocity of C plus D after equals 1.5 over 0.4. So what have we got? 15 over 4. 3 3/4. And the third collision is between B and the combined particle, after which no further collisions. So we could say something similar. We haven't got much room left. Let's move this out of the way there and put another one down here. So after the third collision, which is B hitting the combined particle, B is travelling, after the previous episode we found, with a velocity of 1.2, I beg your pardon, a velocity of 6, but a momentum of 1.2, and it's the momentum we're interested in. So we've got B before, presumably catching up with, because C and D were both moving, they both had a positive momentum and velocity eastwards. So it's going to be like this. Now then, B before is 1.2. We're just taking that directly from over here. So, interestingly, that's the wrong way round. This is the larger one. Whoops. C plus D before. Well, that's 1.5 from here. I mean, it might have been 0.4 times the velocity, which we were interested in, but now we want the momentum again, 1.5. So the total momentum afterwards, and before, as before and after, total momentum of this system, this pair, which is B, one particle, and C plus D, the other particle, combined particle. We're saying C plus, I beg your pardon, B plus C plus D before and after, of course, equals 2.7. In fact, let's say before and after, because we're running out of room. And then after, we have to be careful here, because what's the greatest possible speed of the combined particle? On the face of it, that would be the C plus D particle having all of the momentum of 2.7 and particle B coming to a halt and just being a zero as D was initially. But A is still coming after people, isn't it? That's right. Particle A, at the end of the first episode, the collision between A and B, A after, that was one of the given facts, that the velocity of A after that was 4. So even though it was B that collided with C and D first, if they've said that there are no further collisions, we must make sure that A doesn't catch up with C and D, catch up with B rather. So B can't be travelling less than this velocity of 4 attained by A after the first collision. So we've got A coming after everybody else and with a velocity of 4. So if they're saying that after the last collision there are no further collisions, we must have B and the other one travelling at least 4. So let's assume that. Let's assume B after is travelling with a velocity of 4. So we're talking about 0.2 times 4, 0.8. So B after is going to be about like that. Let's label it properly. B after is 0.8. Has to be at least that. So let's make it no more than that, so that as much as possible of the total momentum of B, C and D is awarded to C and D. So C and D after .9. Okay, so we've got reasonably clearly here, we've got B before 1.2, C plus D before is 1.5, so the total momentum before is 2.7, and since that's going to be the total momentum after, we've got B after, which for those tricky reasons about A chasing after all the others, it means B has to be travelling at least with a velocity of 4, its mass is 0.2, so B after is 0.8, C plus D after is 1.9 therefore, so that these two add up to 2.7 just as these two add up to 2.7. So finally, the greatest velocity for the combined particle is 1.9 divided by their total mass of 0.4. It's not very nice, is it? 19 over 4. Could be worse. Half of 9.5. 4.75. And there we are. Okay, question 5.